Hello there, ATS EVS 105 students. Dr. Shragi here, and we're continuing through Module 5 to start learning about a strategy in modeling called ensembles. Now, just to kind of review as to where we are so far in this module, we had already learned that weather modeling, like the kind of forecasting of day-to-day weather, and modeling climate are two very different kinds of problems. One's an initial condition problem, and one's a boundary condition problem. Both are doable. Both are really complicated problems, but they are doable problems. With a team of climate scientists working together and supercomputing power and stuff like that, they are both solvable problems. I realize that I might have made it sound like weather forecasting is impossibly difficult or climate modeling is really easy. But in both cases, there are strategies that scientists can use that make them, that help them know what the models are telling them, so that they have a way in which they can make sense of what the forecast for future weather is, or what the forecast for future climate is, or so on. Now, so far, everything that I have shown you when we've been talking about modeling weather and modeling climate, has been a strategy known as deterministic modeling. Deterministic modeling happens when, like, a model runs, and we use the output of that model as our forecast, as our understanding of what the system is going to do. And the emphasis here is on this word A, as in a model. We're assuming that this one single model that we're running is going to be telling us what to expect. But that's actually kind of problematic, because as we know, there are problems with the initial conditions in the model. I mean, no matter what, you can't get perfect initial conditions. And frankly, there's lots of models to choose from. Lots of different research groups at universities, lots of different federal agencies all run their own models. How would you know which is the right one with the right resolution, the right size time step? How do you know what to use? I mean, I know that if I ran a different model, or I know that if I ran the same model with slightly different initial conditions, or if I ran the same model with slightly different boundary conditions, I would get a different forecast. This is complicated. Deterministic modeling is, it's a good strategy if you want to just understand one little, if you just want to make one forecast for the future and you're just going to be studying some processes at work. But by and large, when I run a model, I need to understand to some extent how the answer I am getting from the model depends on the choices I made. Choices like, what were my initial conditions, or which model am I using, and at what resolution, and what size time step, and what boundary conditions, and so on. When I only run one model, it's pretty hard to get a sense of any of that. Deterministic modeling has its uses, but that is in general not what we're going to be doing either in weather forecasting or in climate forecasting. We're going to be doing ensemble modeling. Ensemble modeling is a different kind of strategy for working with numerical models. And this word ensemble is pretty tricky. I mean, if I just go to Google and said define ensemble, I get these two definitions that are not quite on the mark, but not as far off as you might think. The first definition is a group of musicians, actors, or dancers who perform together. That's actually closer than we think, except instead of being actors and musicians and so on, it's going to be a group of models that perform together. In ensemble modeling, there are many, possibly very many, numerical models all producing forecasts for the same point in the future. I want to make a 72-hour forecast. If I just run one model, take the current initial conditions and run it out and make a forecast for all these grid points and so on at some point 72 hours into the future, that's a deterministic forecast. If I set up 20 models and they all are slightly different and they all make 72-hour forecasts, that's called ensemble modeling. Okay? Ensemble, it's a group working together, providing all slightly different ideas. The right word for each for each individual model within the ensemble is a member. Each member of the ensemble modeling strategy will end up producing a different forecast, because they all had slightly different something. Slightly different initial conditions, slightly different boundary conditions, maybe they're slightly different models, who knows. It's going to be up to the scientist running the models to decide these things. Each member is going to produce a different forecast. That sounds like a disaster, but actually it's hugely beneficial. This is a great strategy because it helps us understand not only what the most likely outcome is, but what the range of possible outcomes is. And to help understand that, I want to just highlight here We're going to come back to this definition later in the lecture, but here's the actual definition of ensemble forecast from the Glossary of Meteorology. You might not be able to see it on the screen, but the handouts, it should be fine. Otherwise, go to the Glossary of Meteorology online and just search for the definition of ensemble forecast. An ensemble forecast is a set of different forecasts, all valid at the same forecast time. They're all the forecasts for 72 hours from now, or they're all the forecasts for 5 days from now. And we're going to come to the second half of that definition later. But first we want to sort out what we mean for ensemble modeling when we're talking in the context of weather, before we move on and talk about ensemble models of climate. Okay, we know that weather forecasting is an initial condition problem, or an initial value problem. It means the same thing. I mean, the physics behind the atmosphere are well known, but we don't really have any way to know for sure what the initial conditions we should start the model with are. And the way the atmosphere is going to change as the model runs forward and produces forecasts for 24 hours, 48 hours, 72 hours, whatever, is sensitively dependent on the exact initial conditions that you give the model as input. But since, of course, it is impossible to get perfect initial conditions, this becomes a really big problem. I mean, how do you know if the initial conditions you're giving it are good enough? Well, if you have enough computer power, this is actually a problem you can get a handle on. What you're going to do is you're going to run a large number of weather prediction models, that is an ensemble of these models, a collection of them working together, to get a sense of the range and what can go wrong in a forecast. Let's actually work through an example of how you would actually do this. Let's say that we have as much computer power as we need. We got a whole bunch of supercomputers sitting around. Okay. Well, one thing you could do is you could say, I'm going to make a 72-hour forecast, let's say a 48-hour forecast. All right, I'm going to take my computers and I'm going to give them all the current observations that came in, and that's going to be my initial conditions, and that's going to be, we're going to call it run 1. Okay, this is just the term. This is run number 1 of the model. And supercomputer 1 is making run 1, and we'll go leave it alone. Now let's take a look actually at the observations that went into the initial conditions for run 1. Well, one of those observations came from Omaha, and let's just say that the airport in Omaha reported that the temperature was 50. Well, realistically, 50 is not the temperature at the airport in Omaha. It's an estimate of the temperature at the airport in Omaha. But there's obviously all kinds of ways this could be wrong, from just rounding errors, like the right temperature is 49.8 or 50.3, to calibration problems or whatever, or the place where the temperature was taken at the airport wasn't very typical of the temperatures around it. There's any number of things that could go wrong. And so, because we need perfect initial conditions in order for our model to work perfectly, well, because we don't even know for 100% for certain that the temperature at Omaha really is 50, it's possible run 1 is already doomed to fail, because we don't have the right initial conditions at that location. Or, it's altogether possible that the exact temperature in Omaha isn't a factor for the initial conditions at this time. Maybe the first couple, 3 days of the forecast will be just fine, even if we are off by a ½ degree or so. This is a real problem. Sometimes these initial conditions it's very sensitive, and if you don't have them exactly right, the forecast goes strange, and it isn't the way the real world happens. And other times, it doesn't really make that big of a difference, at least not for the first few days. So how would we get a sense of that? Well, if we've got enough supercomputers sitting around that we can do it, let's run more copies of the model. Let's just say, you know what, if the real temperature at Omaha was a degree or so less than this, I wrote it down here as 48.6, let's be more realistic, let's say 49.6. Okay, the temperature was only off by 0.4 of a degree. Alright, let's take our initial conditions that went into model 1, run 1, and change the temperature at Omaha by just a few tenths of a degree. I mean, that's still consistent with the observations. We don't measure the temperature that accurately. And so, okay, well then let's actually make run 2. Where run 2 is a slightly adjusted set of initial conditions based on the observations at the time. They don't normally just change one station. Usually they'll change, 10% of the stations around the country. Or they will remove some of the stations around the country, as if that station didn't report or whatever. The initial conditions aren't really all that different, but they are different. When we have, slightly added little random numbers to the, the temperature in Des Moines is 51, no, let's make that 50.8. Or let's make that 51.3. Let's change the wind observation slightly. We only measure the wind like the nearest 10 degrees. Let's measure it let's say that we were off by a little bit. Whatever. Alright, so we run the model. In practice, those two model runs, run 1 and run 2, might end up producing very similar forecasts for 48 hours from now. They might, but they might not. The two model runs might actually turn out to be very different. You wouldn't think that changing the temperature in a few places by a few tenths of a degree would change the path of a cyclone across the country or to change the speed at which a cold front moves across the country, but sometimes it does. And that would be something useful to know, because when you just had one deterministic forecast, for all you know, you had a strange one. You had one where the forecast, because your initial conditions weren't quite right, you had a strange forecast that wasn't the way the weather was going to be. Well, now if I got two different runs, now what? Well, here's an idea. Let's not just do this twice. Let's buy more supercomputers. And let's say we have 20 runs. Okay, run 1 might be the way the observations really came in, but runs 2 through 20 will be all slightly different initial conditions based on just little changes, and let's adjust the pressure a tiny bit at this station. Maybe they were off by this much here. Let's pretend Des Moines didn't observe, whatever. They just make random little changes like that. And let's say we get 20 copies of the model running. Boy, think about the computer horsepower it takes to do that. Now, we have 20 different 48-hour forecasts. Remember these numerical weather prediction forecasts? A 48-hour forecast probably takes those supercomputers each about 6 hours to do or something like that. So you've got, 6 hours later, you've got 20 models all telling you something different about the weather. But different how? I mean, are they all actually pretty much the same thing? Like they all had kind of the same idea about where the storms were going to happen. They all had about the same idea about how much rain was going to happen. Or are there, and maybe just a few outliers, maybe 2 or 3 of the models went a strange way and they have totally different ideas about where the storms are going to happen? Or is the spread huge? In fact, all 20 of them ended up with very different ideas about the weather. Oh, we're going to need to have some way of figuring that out. Now, in practice, there's a lot of tools that atmospheric scientists and climate scientists and so on can use to figure out, once they have a set of answers from an ensemble of models, trying to figure out what they mean. But the one that's interesting and graphically useful and helpful for things we're going to be doing later in the semester is a technique that is called spaghetti charts. We're going to produce spaghetti charts that are showing us what happened in these model runs. Now, what I want to do here is I want to set this up by showing I'm actually recording this on March 3rd, 2016, and this is actually the model output from that day. Now, here's a map. This is actually the current map of observations of a quantity that meteorologists care about called 500 millibar height. You do not, in the context of this course, need to know what 500 millibar height is. It's just a thing, okay? It's something meteorologists need in order to make good forecasts and so on. It is a property of the atmosphere above the surface of the Earth. Don't worry about the details. Look, it's a lovely map of it. It's got a key, all that kind of stuff. These are the actual observed values at this time. Now, rather than work with this pretty colorful map here that has all this different things on here, see how there's little lines that separate the different areas of colors? Each color represents a range of 500 millibar height, and there's little lines that separate them. Those lines are called contours. Let's just pick 2 of those contours, and we're going to take a look at them and see how they are changing in the models. So like here is, at the present time, those 2 thick white lines that I have on there, which are actually then just represented on the plot that came from the National Climate Prediction, National Center for Environmental Prediction, NCEP. Those 2 kind of thick, one's kind of green and yellow and one sort of orange and yellow, are the 2 lines that we're going to be working with. The other 2 lines that are on there, by the way, those green lines that are labeled climatology, don't worry about them right now. We're talking about the 2 fatter lines that sort of have yellow in the middle of them. Now, in this particular case, NCEP, the National Center for Environmental Prediction, ran this morning the model 21 times. You can see the number down there in the bottom. In other words, there are 21 members to the ensemble that we're looking at here. Now, if you actually zoom in on the map and look closely, you can see that what looked like kind of a fat bluish line with a yellow line in the middle of it is actually made up of a whole bunch of strands. What that is they are drawing where 21 different models all think that line should be on their depiction of the current conditions of 500 millibars height. Okay, again, don't worry about what 500 millibar height is, but you can see that the 21 models have pretty much the same idea. Now, you can see actually over like North and South Dakota, there is a little variability there, where apparently as they tweaked, for the 21 different sets of initial conditions, this is one of the places where there were some changes, okay? But in general, the 21 sets of lines are practically right on top of each other, okay? The 21 models are starting with 21 slightly different sets of initial conditions, but they're all pretty much the same. And so when we take this plot here, and we have those two contours that we care about, and we're going to start running our model 21 times. 21 different racks of computers are plowing away at this, and they get a 24-hour forecast. So this is the forecast for March 4th, 2016, and we have plotted those same two contour lines for our 21 different models. There's like 42 lines on this diagram depicting what those 21 models each think the 500 millibar height should look like. Now if we zoom in here, this place that I have in a blinking red circle there shows that you can see that there are some differences. The 21 models have slightly different ideas of what the 500 millibar height pattern looks like. Some think the line is a little farther to the north, some think the line should be a little farther to the south, etc. The forecasts aren't in perfect agreement. On the other hand, actually, in most locations, the 21 lines that are the 21 places they think those lines should be are basically right on top of each other. Here, the 21 forecasts, like in the area I've circled in red here, are all basically the same. I mean, there may be some small differences that came about, remember we started with different initial conditions, but actually, like in this case, this contour line as it crosses Utah and Colorado and so on, is all basically the same in all 21 models. We have pretty good confidence of what's going on here. In fact, I'm going to give you a vocabulary word here. There's consensus. The 21 models are in consensus here, that 24 hours from now, that's what the 500 millibar pattern across like Nevada and Utah and Idaho and Colorado and so on is going to look like. The models are in good consensus there. We gave it 21 different sets of initial conditions, and they all came up with basically the same 24-hour forecast. Brilliant. Now, if we go farther into the future, like 48 hours into the future, so this is the March 5th, 2016 forecast here, the differences in the 21 members are starting to get a little more apparent. I mean, if I zoom in here, yeah, across like Kansas, Oklahoma, Missouri, and Arkansas, the places I have circled right now, well, there, those 21 sets of red contour lines there that are where the models think the heights are, they're actually in pretty good agreement in that area. There's some slight difference, but actually for 48 hours into advance, this aspect of the forecast anyway looks pretty good. Looks like the 21 models are in consensus. On the other hand, what am I going to make about the East Coast here? I mean, this area I have circled here, well, actually, I mean, all 21 versions of the model seem to agree that there's going to be a little dip in the contours there. A dip in the contours like that is called a trough. Okay, that's a term that you're not going to learn in this class. That's actually an ATS 113 thing. But that little dip in the contours is called a trough. We're just going to use that as a useful vocabulary word here. You can see all 21 sets of those little blue curves here that show where each of the 21 models in the ensemble, each of the 21 members in the ensemble think the trough will be. Well, they all think there's going to be a trough. But they do have some pretty good disagreement as to where the trough is going to be. There is consensus that there's going to be a trough in the 500 millibar height contours, but where exactly it is, there's, maybe a couple hundred miles of range here. Okay, so if you're a forecaster here, you have great confidence that there's going to be a trough. None of the models thought there wouldn't be a trough, but exactly where it is, well, it's in the middle Atlantic states. But I mean, if you really need a high quality forecast, this is not going to do it. So 48 hours into the forecast, we're pretty confident about what the weather's doing in the area down here, Arkansas and Oklahoma and Kansas and so on. But we're a whole lot less confident about what's going on over here in the mid-Atlantic states. But on the other hand, just because we're not confident about what's going to happen, we do actually have a pretty good sense of the range of outcomes. No matter what, we know the pattern looks something like this. None of them are radically different. Okay. Let's go farther into the future. Here's 72 hours into the future. So this is 3 days out from when we started the model. The model has now been running and simulating the weather 3 days out in our numerical model. And the differences are getting even more apparent. On the other hand, there actually is still some pretty good agreement in terms of the broad features of the atmosphere. For example, all 21 models, if you look closely at each of their little curves there, all 21 agree that there's this big feature called a ridge across like the north-central United States. This kind of feature where the contour lines bow to the north and then turn back to the south. All 21 models agree about that. Exactly where it is, you can see that there's a spread of maybe even as much as a couple hundred miles. But at least 72 hours in the future, we know, 21 different models, given 21 different sets of initial conditions, are all in agreement that 3 days from now there's going to be a big ridge across the north-central United States. I have pretty good high confidence that that's going to happen because the models are in consensus. And for that matter, if we look at the eastern half of the United States, in like the Northeast. Well, I mean, all 21 models certainly agree that there's going to be a big trough across the eastern United States 3 days from now, where the contour lines have dipped to the south like that. So I have high confidence that's going to happen, but boy, there's an awful lot of uncertainty from one model in the ensemble to the next as to what it's going to look like. Honestly, though, this was actually a pretty good day for the models. In fact, if I look further ahead, this is the 96-hour forecast, this is the 4-day forecast. Actually, you're going to see it gets a lot worse than this. I mean, you can see there's getting to be quite a lot of spread between the different model members. But actually, they're all pretty good. I mean, they all have the same basic broad features. If you needed to know exactly where that trough was or exactly where that ridge was, well, that might be a little bit of a problem. But if you're just talking about the broad patterns across the United States, boy, even at 4 days, the forecast looks pretty good. And then it all goes to hell. I mean, like, see, here we go. Here's a 120-hour forecast. That's the 5-day forecast. And wow, I mean, these contour lines are all over the place. Clearly, all the models have very different ideas about what the 500 millibar pattern is going to look like. All of them, when they draw their contours to what the pattern should look like, it just makes spaghetti. It's all over the place. Although actually, in fairness, this is not a disaster. For a 5-day forecast, this is not bad. All of them actually do have a surprising amount of agreement about, like, say, the eastern half of the United States. See how, like, up through Arkansas and Indiana and over towards Pennsylvania? Yeah, the contours, I mean, there's a spread of a couple hundred miles between the farthest north and the farthest south of those red contours on there. But actually, they're all still pretty well grouped. Way better than, like, over the Rockies, right? Where those blue contours are just spaghetti at this point. You can see where the term spaghetti comes from, right? These are clearly just, it just refers to the fact that they get to be a mess. And trust me, they get to be a really big mess. It just so happens today, it really, on the model runs, it took until about day 5 before they really went to heck. But if you go farther into the future, like the day 6 forecast, or the day 7 forecast, or the day 8 forecast, you can see the contours get messier and messier. They get to be more and more spaghetti. The 21 different models, all, even though their initial conditions were practically the same, in practice, by the time they've integrated out to the day 8 forecast, which is what, I don't know, 192 hours out, they're starting to have a pretty big range of ideas about what the weather's going to be doing, what the pattern of, in this case it's 500 millibar heights, is doing. And if you go even farther out to like day 10, it just gets to be a messier and messier set of spaghetti contours. By that time, the model has virtually no value at all, virtually no skill, to use the right word. So when the members of the model are producing forecasts that are all in pretty good agreement and the contours all pretty much lay right on top of each other, we can have pretty good confidence that the models are predicting what will actually happen. The term of art is that the models are in consensus. On the other hand, when the members of the model are producing wildly varying forecasts and they all just disagree in all kinds of different ways, we have very low confidence that what the models are predicting is actually going to happen. Now, in the case of ensemble modeling of weather, the members of the ensemble, in this case like the 21 different models that we ran, usually are only different in terms of their initial conditions. That's usually the only thing, like the National Centers for Environmental Prediction, that's the only thing they'll have changed from one model run to another in their ensemble. But, well, that sounds lovely for weather. Weather is an initial condition problem. Little changes to the initial condition will make a big difference to the forecast. But what if we switch our story here to climate? What if we want to make an ensemble model of climate, where we're trying to make a numerical model predicting what the climate is going to be like 100 years from now, or 250 years from now, or 100 years from now if we double the amount of carbon dioxide, or something like that? Well, remember, one of the key things we've learned so far in this module is that in climate modeling, the initial conditions don't really matter. It isn't an initial condition problem, it's a boundary condition problem. Well, if we turn back to our American Meteorological Society Glossary of Meteorology definition of ensemble forecasts, let me actually just reproduce some of the text there in case it's too small to read. The forecast in an ensemble may have different initial conditions, boundary conditions, parameter settings, or may even be entirely independent numerical weather prediction models. Okay, so when we were doing an ensemble forecast of weather, we had different initial conditions between each member of the ensemble. Okay, well, but initial conditions don't matter in a climate model. So in a climate model, we're going to require that the model run many times, each with different boundary conditions. Now, what are boundary conditions in the model? Remember, they're things out external to the 7 primitive equations things that are driving the climate that are external to like the motions of the atmosphere. They're things like carbon dioxide concentration, or the output of the sun, or changes in the orbit of the Earth, or something like that. These are going to be what we're going to change. We're going to run a whole bunch of different climate models, this time with slightly different amounts of carbon dioxide, or slightly different albedos of the surface of the Earth, or something like that. We'll provide it with different input. Remember, boundary conditions are an input too. They're just not initial conditions, they're boundary conditions. Initial conditions, remember, are ones that's what we're trying to solve for. They're values that then we solve for, you know, how they change. We give it the temperature, the pressure, the winds, and then at some point in the future we solve for the temperature, the pressure, the winds at 48 hours or whatever. Now we're giving it boundary conditions, and we're seeing how the climate changes. Or, I mean, according to this definition here, one way that we could do an ensemble of model runs is to use entirely independent numerical weather prediction models. We could run the model run created by scientists at Princeton next to the model run by the scientists at the UK Met Office in London, next to the model run by people at the National Center for Atmospheric Research in Boulder, Colorado, and we could have all these different models, all trying, we could see if all these different models give us the same answer. That sounds good. There is another one in here, by the way. It says we could run with different parameter settings. That is something for a future unit. Let's not worry about that right now. So we could run with all these different models, and all these models are based on the 7 primitive equations, but they were written by different teams, sometimes for slightly different purposes. They'll have different resolutions, they'll have different sizes of time steps, there might be slightly different approximations to some of the 7 primitive equations. They should all work, but that doesn't mean they all produce exactly the same answer. Hopefully, as I was telling you about this idea of ensemble modeling of climate, something occurred to you. I'm hoping you said, wait, Dr. Sharkey, didn't you tell us that running a numerical model of climate takes weeks or even months on a supercomputer? Yes, I did. And now you're saying, you're saying we need to run lots and lots of climate simulations in order to understand the future climate or whatever? Yes, that's what we have to do. We have to run our climate models lots and lots of times, each of which might take months on a supercomputer. Holy smokes. Well, nobody said it was going to be easy, okay? Understanding climate is a complicated problem. And yes, we are going to be talking about the fact that there are going to be literally dozens of different forecasts of future climate based on different boundary conditions or different models or whatever, so that we have an ensemble forecast of how is the climate going to change if we double carbon dioxide, or how is the climate going to change if we start making certain changes in our emissions now. Nobody said any of this was going to be easy, but we have to also be smart about it. We can't just go and send the researchers at National Center for Atmospheric Research in Boulder, and the UK Met Office in London, and ECMWF, the European Center for Medium Range Weather Forecasting in, I don't know, Darmstadt, Germany, or wherever they are. Hamburg, that's where they are. And the model groups at lots of different universities. We can't just all send them out there to just do this. We're going to need a plan. Because it isn't like we've got enough supercomputers to just kind of play with these models here, okay? We're going to need a plan. Everybody needs to run the model in a sort of systematic way. And that's where we're going with this next. We're going to show that we're going to come up with a set of scenarios. Scenarios are going to be defined as like a set of defined boundary conditions. We are all going to run all these different models. Let's run them all with twice as much carbon dioxide as the pre-industrial level, and this many watts per square meter of shortwave radiation from the sun. Or we're going to run them all this way with this set of parameters or whatever. So that then it's easier to compare. So that we can compare the output of the models from Colorado to the models in Hamburg, to the models in London, to the models in every research group. Okay? And that way we aren't like wasting effort. Oh, this group actually did it for 1.5 times as much carbon dioxide, whereas this group actually did it for twice as much. No, we want to be able to compare them directly. Alright, so we're going to, in the next lecture, be talking about all these different scenarios that we have to define so that we can, in a systematic way, figure out what these ensembles of climate models are telling us. That's in the next lecture. Before we get there, though, I wanted you to answer a couple quick questions here. Question 1. The main problem with relying on a deterministic modeling strategy is that the forecaster has no way to know in advance, A, if the weather is changing at all, B, whether or not the 7 primitive equations actually apply in this current situation, C, if he or she has enough computer power to run this large set of models, or D, if the inputs of the model are accurate enough, are adequate to produce an accurate forecast. Oh, what is the problem with deterministic forecasting? Make a choice from one of those four and get a little feedback before you move on to question 2.